coming to Austin Dixon's master's thesis defense. My name's Lee Orff. I'm a scientist at SIMS, and I am Austin's research advisor. Steve Ackerman is Austin's academic advisor. Austin came to me 2 years ago from the University of Oklahoma, where he got his bachelor's degree in meteorology. He came to me as someone who's extremely interested in supercell and observations and tornadoes, but he came to me as someone who was maybe a little bit less interested or experienced with the modeling aspect of it, but once he's been looking at my data for a while and knew that he wanted to do something to look at supercells through the lens of radars, but looking at the numerical data. So this is basically the kernel of his thesis, is to take radar applications to numerical data. So he built himself a radar emulator, and he swept it through some of our data sets to look at features near the updraft of the storm. And he's going to talk about his research. And he also, I wanted to say, great news for Austin. He's already got a paid PhD position at the University of Oklahoma that he starts in the fall. So I guess without any further ado, Austin, take it away.
Thanks, Lee. All right, so like Lee said, the basis for this paper and research was emulated radar observations of specifically near-updraft vorticity in the simulated supercell. And that's actually the simulated storm in the background there. It's a very detailed rendering of it. But the motivation for this was Lee conducted a simulation, what was it, 2014, I think. And it was a 30-meter resolution. And I've got more details on the exact simulation here in a minute. But in the preliminary paper that they put out on this simulation, they discovered what they called the streamwise vorticity current. And it was pretty quickly apparent that this thing seemed to have an influence on the low-level updraft in the supercell. And that worked to enhance the low-level updraft and also the low-level vorticity. And of course, when you enhance the low-level updraft and you enhance low-level vorticity, you also enhance your probability of forming a tornado. The SVC itself forms more than 15 minutes prior to tornadogenesis in this simulation. And if it does have a positive impact on tornadogenesis, then obviously detecting this feature on radar would be very beneficial to the operational forecasting process. So just some background on the simulation itself. It was run on the Blue Water Supercomputer, which is at University of Illinois, Urbana-Champaign. It's a massively parallel computer with over 22,500 compute nodes, each with 16 floating point processing cores and 64 gigabytes of RAM. The simulation was on a 2200 by 2200 by 380 grid with 30-meter grid spacing, and that's in 3D. And when you're saving data frequently on this grid at that resolution, you end up with about 100 terabytes. And if you think that's a lot of data, you should see some of the new simulations. It was run on Cloud Model 1, which is a 3D non-hydrostatic model for studying atmospheric processes. And this is the sounding we used. It's a model forecast sounding from the RUP. It was taken off the right flank of the supercell that produced a long-track EF5 tornado in El Reno, Oklahoma. That was on May 24th, 2011. All the thermodynamic and kinematic variables in this profile are way up in the upper quartiles. We got 5,000 joules per kilogram of surface-based cape. The LCL is almost sitting on the ground. The 0 to 1 kilometer storm relative velocity is 371 meters squared per second squared. This is a textbook loaded gun sounding.
What's the red in this cyan temperature?
So the red is the observed temperature, and then the green is the virtual temperature correction. So just to go over some basics of supercells real quick to fill in those who don't study these on a daily basis. This is kind of what they typically look like on radar, and they have kind of this kidney bean shape. You have the hook echo, which is this guy, and the hook echo forms because the storm is rotating And so you have the precipitation that gets wrapped around the backside of the storm. The main core of precipitation creates what we call the forward flank downdraft. And so you see this big area of divergence here. The updraft is centered basically right underneath the tip of the hook echo, about right here. And this whole area here is warm inflow into the storm. They also, in the conceptual model, they have what's called a rear flank downdraft, and it's been shown many times over the years that a lot of supercells do have this feature. Interestingly enough, in our simulation, it's not super present until after the tornado really gets going. We won't really get into that much, but it is interesting to note. And so in these storms, you kind of have flow that goes like this. You have flow that comes out of the forward flank downdraft into the updraft and wraps around itself here into the mesocyclone. So the SVC, this is the hook echo here, so your forward flank precipitation is up this way. The SVC stretches out of the forward flank precipitation out down into the updraft this way, and it wraps around the backside of where the tornado eventually is. And we define this feature as a persistent tube or streamwise vorticity. It's located along the forward flank downdraft boundary, and it flows rearward along the forward flank downdraft boundary, eventually into the updraft. Yes.
Austin, what's the adjective streamwise mean here for vorticity?
So the vorticity vector is flowing, pointing in the same direction as the horizontal wind.
Okay.
Yeah.
Helical flow.
Yeah, exactly. We don't really understand yet if this is solely baroclinically generated or kinematically generated. I suspect it's a combination of both, and we'll get into some of that here in a little bit. But just want to talk about how this feature appears to influence the storm preliminarily. So this is at time 3,000 seconds into the simulation, and this is about when the SVC forms as we kind of define it. And at this time, the low-level updraft is about 2.5 kilometers, 2.4 to be exact. And then over the course of 800 seconds, which is a little less than 15 minutes, it lowers by over 500 meters. And this is one of the primary impacts of this feature that we've seen so far, is that it really works to lower this low-level updraft and strengthen it as well. Vertical velocity does increase by around 10 meters per second during this time as well. And this most likely results in a positive feedback that just continues to intensify this area of the storm. At the same time, we also have this negative pressure perturbation that shows up, and this is obviously associated with the updraft, but you do have this interesting bend out this way towards the forward flank, which kind of seems like it may be associated with the SVC. We don't really know for sure yet. We need to do more analysis on whether or not it actually rotates fast enough to create cyclostrophic pressure deficits. But this is basically the same period of time, and this is actually a less amount of time. This is 3,400 seconds, and this is like 3,630 down here, I believe. But in that time period, you have a 15 hectopascal pressure deficit between the two. And you also have, you can see the lowering of the updraft here as well. We don't have the height references in this one like we did on the other one, but you can tell by looking at it that it's just longer on the bottom. Yes?
So you're not sure whether it's a cyclostrophic pressure perturbation. What would be the alternative? How else would you sustain that kind of pressure perturbation?
Yeah, I mean, that's a good question. I really personally think it's cyclostrophic if this bend truly does go through the SVC. I mean, it could just be that the updraft itself is kind of bent like that, but just based on what I've seen in this simulation, I really believe that it's associated with the SVC. We just haven't proven that yet. So this is another look at this feature. We're pretty sure it's co-located with a vertical vortex sheet, and at a certain point, you start to get vertical shearing along the SVC, and you end up with all these smaller mesovortices. And all of these mesovortices train into the updraft, and I've called that the mesovortex train, just to give it a name. And if we look at another view of this, so this is at 3,000 seconds. Tornadogenesis occurs at about 3,800 seconds. And so this is, if you notice, all these tubes are fairly spread out here. And if we go forward 500 seconds, you really see things start to wrap up. And like we said, this SVC starts really influencing the storm about this time at 3,000 seconds, and then you start to see that updraft strengthen and lower, and things kind of start just getting really tight underneath the storm. And if we go another 200 seconds, here's more of these mesovortices here. And what actually happens is, as this area of vorticity and vertical velocity gets stronger, you start to see these mesovortices show up, and eventually it's as if the storm kind of reaches a critical point. All these mesovortices start to conglomerate in one spot, and those eventually culminate in a tornado. This is really interesting because there's no obvious trigger. It's like all these things come together at the same time, and all of a sudden we've got a tornado. And then it's this vortex right here, I believe, that is actually the tornado. But this is 3780. You see all these vortices here. This is 3830. Now they're all kind of packed in here, and we've got the tornado. All of this appears to be a direct result of this SVC, and what we are trying to do, or what I've tried to do in this project, is create radar images of the SVC in both horizontal and vertical cross sections, and see if we can actually see this thing on radar and try to identify it, improve tornado forecasting. So we built this radar emulator. This is a lot of text, but I'll give you the synopsis. Basically, it's a Python-based software. It converts simulated reflectivity data and velocity data into polar coordinates. You can do plane position indicator, or PPI, and range height indicator, or RHI scanning. We don't actually simulate a radar beam. That's why we're calling it an emulator. So it doesn't simulate a beam of radiation. It basically just puts the image in polar coordinates, puts it into boxes, just like a radar image would be. And so we're not simulating radar, we're just making it look like radar as much as we can. You can define all the radar specifications that you want to, pretty much. You can put it anywhere you want. You can define how far it goes out, how small the bends are through range step and azimuth step, the elevation of the radar, the azimuth angle, all that stuff. And since it's obviously not a simulated beam, it's just an emulator, we don't have issues with curvature of the Earth. There's no range folding, no biological returns, no anomalous propagation, no terrain influence, no side lobing, no ground clutter, or any other erroneous returns that you might get on a real radar image. So it's likely that the radar images you're going to see are probably generous as far as the detail and things that can actually be seen, especially at the very lowest levels. But we're just trying to get an idea. And so these are the specs that I chose for the radar. So we did WSR88D, because that's the operational NextRad system right now. That's what people on a forecast desk are going to be looking at. The lowest elevation angle they use for NextRad is 1/2 degree. They scan every 1 degree, or the beam gives data every 1 degree, and the bends are every 250 meters. The other one I chose is RAXPOL, which is a mobile research Doppler radar at the University of Oklahoma. It's an X-band radar, and it's also 1/2 degree of elevation angle with a 1 degree azimuth increment. But the range increment on that is actually 30 meters, so it's super high resolution.
So are you using the cloud microphysics to emulate the radar signal?
No. So it's strictly just taking the velocity data is actually radial velocity. It's been converted using, to and away equations. But the reflectivity has basically just been converted to polar coordinates and made it look like radar.
And the reflectivity is coming from where, because you need a particle size distribution for that.
Well, so it's coming from the model data.
Okay, the model does have.
The model has
Yes.
code that generates reflectivity from the mixing ratio.
Yes,
Right.
but the radar emulator itself is not like bouncing off of particles.
No, right, yeah.
Yeah.
Sweeping through.
So this is just an example image, and I wanted to circle this area because this is kind of the region we're going to be focusing on. So here's the hook echo, there's the forward flank, and then if you can see this little stringy thing here in the reflectivity, that's the forward flank downdraft boundary. So that's the area we're going to be focusing on the most. So this is at pre-tornado genesis time. This is at 3600 seconds, or 3610, excuse me. Again, we've highlighted the area, that's the forward flank downdraft boundary. This is at rack pole resolution. This is at 88D. I've looked at a lot of 88D images trying to see if this is actually visible on there. Most of the time it's not. I think this is a very generous estimation of this area of the storm for 88D. Most of the time when supercells get that, they would have to be really close to the radar, which they are in this case. But you know, most of the time you're probably not going to get that information from an 88D. Kelvin, did you have a question?
I was just going to ask, what's the distance from like your cone of silence region to the edge of the image,
To here?
or to the bottom left, like the edge, your last?
Oh, from here to here?
Yeah.
I
Scale-wise.
believe it is 10 kilometers.
Okay.
Yeah.
So it has to be right on top.
Yeah,
of it.
so it's pretty close.
Are there corrections you can make using what you've developed, Austin, for real radars? In other words, you could say, boy, wouldn't it be nice if the radar were in this location with respect to this point in the storm? Let's apply this pseudo correction. Can you do something like that?
I'm not sure. I mean, the goal of this was really so hopefully some field researchers see it.
Hmm.
And, you know, we're basically, eventually we'll get to the slide where I talk about the best places to put the radar. But really the idea is that I want field researchers to see this and say, hey, in our simulation we could see the radar best from this spot. You should take Rack's pole out there and try to do the same thing and see what you see. That's kind of what we're going for. But does that answer your question?
It does a little bit. That's a purely operational way of actually moving radars. But I wonder if there isn't a way that you could just take the coordinates of the actual position of the radar and the feature in the storm that you're looking at and say, if we could change that relative position, and we can change it in some systematic way that's based on your emulator,
Yeah.
maybe you could recreate from the real signal something that you might be missing because
Yeah.
of that position.
Yeah, it's an interesting idea. I mean, I'm not a radar engineer, so I have no idea if that's possible or not. Yes, sir.
Alternatively, you could just take your simulations and move it further away from the radar. So if you looked at cases where you anticipated seeing this,
Yeah,
put
yeah.
the simulated radar the actual distance away to see what you see.
That's the inverse of what
Yeah.
I'm suggesting.
Yeah,
that's
we
right.
can move this radar anywhere we want in the simulation, so yeah, it's definitely possible. Moving on to velocity, so this is ground relative velocity. Again, left is Rack's pole, right is 88D. There's no real obvious evidence of the SVC here to me. I mean, you do have the zero isotop, and it just so happens to be co-located with the SVC in this case, but to me, you know, we know where the SVC is from the simulation. But if I'm an operational forecaster looking at this on radar, I don't think I can objectively look at this and say, oh yeah, there's the SVC. It's just a zero isotop. But we would have to get more into that to be sure. I'm not positive. I need to talk to the operational forecasters more about this.
And the zero isotop is going to be very sensitive to where you've got the radar placed.
Exactly. Yeah, and I've got more images later on where that's going to change.
But what about in 3D? What if you have a box around that area? Don't you see something more than just a line?
Yeah. So I've got RHI scans of this where it looks a lot different. It's not a zero isotop. Well, it kind of is, but it's different. So this is storm relative velocity. Again, it's basically the same story. You do have some couplets right here that are kind of random. There's not really much to it, but one interesting thing to note is if you see these lines in the velocity, these are actually vorticity tubes out in the forward flank. I have talked to some people who work on the field radars, and they have seen these before, which is encouraging. I don't really get into that too much in this study, but it is cool to see those.
And they don't show up on any ET worth of arm?
No,
Yeah.
definitely not.
Too small.
So this is an RHI scan of pre-tornado genesis. This image shows, so the white dot is where the radar is, the black is the radar beam. So it's here and it's pointing to the left across the forward flank downdraft boundary. This is a reflectivity image. If you notice, there's this big billow here. And I would assume that's because in the velocity scans, we have a strong inbound flow here. This is 40 plus meters per second with pretty strong 25 to 30 meter per second outbound winds going over the top of it. So I assume that there's some kind of gyre going on there, which would make sense because we're scanning through the SVC, which is creating this big reflectivity billow here. It's about 2.5 kilometers tall in total. And if we compare the velocity data to a cross-section of streamwise vorticity, you can kind of see like the bent over shape here in the velocity data, that, it's comparable to the shape of the streamwise vorticity cross-section. The structure of this and the velocity signature that's shown is really similar to what you see in RKW theory for gust fronts along the leading edge of linear thunderstorms. And they basically proved that a rotor exists when you have these features. And that's good that we're seeing this because that shows that, we can show on radar that there is a rotor there. Which we know there is in the simulation. So now we're at time of tornado genesis. And again, this is the forward flank downdraft boundary. Same with the 88D data. And again, this is pretty nebulous here. It's not real obvious whether that's important or not. And it basically looks like the same thing at first glance, but if you zoom in, you'll notice these little nodules here along this boundary. And if we go to velocity data, and we zoom in on that, now here's a couplet, here's a couplet, here's a couplet, here's a couplet. And we're starting to see these vortices show up in the radar data. And they're still pretty I don't know, you would have to really be scrutinizing that data to get those nailed down. But if we look at storm relative velocity, it gives us a little bit different picture. They show up again, and if anything, they look worse. So, I don't know, I think at this point, maybe we should try moving the radar to see if we can see them better. So if we do that, well now, so you can see them again here. This is the tornado, actually. If we zoom in on that, now we've got a lot more obvious couplets showing up there. And
Austin, isn't partly that due to your color map choice? I mean, essentially when you change from storm relative to ground relative, you're sort of shifting around the color map.
well,
In a
so
sense.
this is storm relative
Right,
with the radar up here.
right.
This is also storm relative with the radar
Okay.
down here.
Yeah, it is, yeah.
So it's the same data,
Got it.
just a different radar location.
Fair enough.
So what's really cool about this is there's been field observations of this exact same phenomenon. This is from a paper by Jeff Snyder in 2013. This was a large tornado event that occurred in May of 2008. And this is reflectivity on the left, this is velocity data on the right. And all these circles are circling the couplets. These two here look really similar to what shows up in this data. And that's just really gratifying to see that the real data is looking a lot like our emulated data.
That top one, a couple of two, it's a little harder to see.
Yeah, some of these circles were kind of like, eh.
The Snyder is the one who circled those.
Yeah.
Yeah, right.
Yeah,
So-
exactly. What do you
Something I'm not today.
What do you mean?
He sees them.
Thank you for making that point. So this is another RHI, tornado genesis time. The most interesting thing to note here is the billow's gotten a lot smaller. This is lowered by almost 1 kilometer. And if you notice, this inbound velocity here is a little bit weaker, maybe about 10 to 15 meters per second. The outbound velocity is a little bit more organized, but overall the inbound is a smaller area, it's smaller magnitude. And so, you could be getting less of a gyre effect here, which would lower the billow, or the alternative is, since this over the top, or the outbound velocities here are more organized, it could be knocking down the top of that rotor more too. I'm pretty sure the SVC is actually a little bit stronger at this point than it was in the previous image, so I would assume it's got more to do with this. Because the updraft is stronger at this time, it's lower at this time, you've got stronger inflow as well. So my hypothesis is that this is actually just kind of getting sheared off on the top as opposed to being a smaller gyre effect. So just comparing the streamwise vorticity to the velocity data, this is a little bit more classic Kelvin-Helmholtz billow here. And again, we've got the stronger inbound and outbound flow, so we're going to have more shearing across that boundary, so it makes sense that we have a lot more Kelvin-Helmholtz looking feature there. Magnitude's pretty much overall the same, but all right, now we're moving on to tornado maintenance. The actual structure of the storm is quite a bit different at this point. The hook echo is a lot thinner, which is pretty typical in nature for these storms that have big violent tornadoes. You often see the hook echo get really stringy, especially with really high resolution data. Here's the tornado. We got the nice donut hole with no rain in the middle, although there is rain in the middle, but not as much as what's around it. And this is the forward flank downdraft boundary, which is now kind of reoriented to the northeast as opposed to being more north-south. And we actually get a lot of that showing up still pretty nicely in 88D. Again, I think a lot of this right here in the weak echo region is fairly generous, but we are right on top of the radar. So here's the velocity data during a tornado maintenance phase. Very obvious, strong tornado going on here. At this point, it's producing winds in excess of 90 meters per second, which is over 200 miles an hour. That's the definition of EF5 strength. So we've got this jet coming from the radar, towards the updraft region, and obviously this is not the zero isodop anymore. The forward flank downdraft boundary, like I said, it kind of reoriented itself more to the northeast, so it's kind of pointed directly outbound from the radar as opposed to being a little more to the west of it. And here's the same image in storm relative velocity. And here's where it gets really interesting. So this is the emulated radar image on the left, and this is an observed case from Paducah, Kentucky, just a few months ago, and we have a very similar looking kinematic boundary here. And this is the location of the tornado where this red square is. And if you notice, I mean, these two images look very, very similar. And it's really cool to see this in nature now, because we weren't sure, especially this is an 88D radar. This is the emulated 88D image. We weren't sure if we were really going to be picking up this type of stuff with the 88Ds, and then people started noticing this and sending it to us, and it was really exciting to see this. So it's like, again, it's very gratifying to see this stuff showing up. Another RHI during tornado maintenance. Interestingly, at this point in the simulation, everything is almost like steady state. The forward flank part of the storm is very smooth, and all of the density perturbation data and all that stuff. And you notice the reflectivity and the velocity kind of reflects that. It's not as strong. The billow is pretty low. The forward flank, the weak echo region looks a little bit more quiet. There's just not as much noise, which is interesting because this is like the most violent time of the storm. And so it's almost like once this tornado really gets a hold in the storm, the storm is just chilling. It's in steady state almost, which is really interesting.
Never heard a tornadic storm described as chilling.
Yeah, but things have kind of conglomerated in your prior set of slides, right? There's a whole line of little vortices and streamwise vortex tubes that are connected to them, and suddenly when you get your tornado, they're all consolidated into one. I mean, that does sort of suggest that things have quieted down. They've kind of, filtered through all the noise and found something.
Right, and we don't see the mesovortices along the SVC like we did previously. A lot of the vorticity that feeds the tornado once it gets going is actually coming from out here in those vorticity tubes that I pointed out earlier. Yeah, it's really interesting. It's very smooth and very steady once the tornado gets going. Another comparison to the streamwise vorticity. Now this is really weird. It gets really tall. It's not nearly as coherent. And with everything else being as smooth as it is, you would kind of figure that this would be just smooth too, but I think because we've got, less inbound, outbound going on here, it's just not quite tugging at the environment like it was before. It's a little bit less organized, but more organized at the same time. It doesn't really make sense. If you look at 3D images of this part of the storm, it all looks super smooth and quiet, but when you take cross sections of it, it's a lot noisier. And also interesting to note that it's kind of started to interact with vorticity from the upper levels of the storm as well. This is about, the top of this is about 1 kilometer, I think, and now this stuff is coming down and reaching as well. I don't really know why that is, but it was something interesting to see. So now we're gonna get into a little bit of text, but it'll get interesting again, I promise. The SVC is gonna be difficult to detect with ADAD in most cases. The Paducah case, it was really cool to see and interesting, but that thing was right on top of the radar, moving in the right direction. It was just a very ideal situation to get that data. We have noticed a couple more instances where we've seen a similar presentation on ADAD. We're probably going to be really having an eye out for that sort of thing now, but even still, it's going to be a kind of a random best case scenario type thing when that happens, and that's not good enough for operational improvement. I think the most fruitful base radar pursuit of the SVC is going to be in the research sector for the time being. The 88D network really needs an upgrade. It's just behind in terms of temporal and spatial resolution, in my opinion. But of course, that requires billions of dollars. It'll happen eventually, but who knows when. The three-dimensional nature of the SVC is going to be tough to pick out with 2D radar data. But I think if I was going to design a field project to study this feature, I'd want 2 mobile radars, one doing RHIs through it and one doing VPIs. And you can get the most information about it in all dimensions, and just compare the two like we did here in this presentation. I think the over-under signature is probably the closest thing you're going to get to the SVC with RHIs. We still need to compare this to a non-tornadic supercell to see if it looks the same. It may not. That'll bring some interesting twists to the project. But let's see. PPI scans provide valuable information when they're really close to the updraft, and it seems like based on what the studies that I did, if you have the radar kind of ahead of the storm motion and in line with the storm motion, you get the best information about the kinematic boundary itself, and then if you put the radar more out to the east of the storm motion, you get better information about the MBT. So it really depends on, I guess, what you were trying to study that day, where you placed your radar, where you chose to follow alongside the storm. You get more vertical information about the SVC with RHI scans. Obviously, you can get the cross sections and see the full scale of it, the full structure of it. But you really don't get any information about streamwise vorticity using radar, obviously. You kind of have to infer it's there. But I believe there's still valuable information to be gained about its structure and evolution just by looking at the radial velocity data. And also, I think the most accurate scanning you can do with the RHI is going to be perpendicular to that boundary. And that's so you don't get any diluted returns in velocity if you have it at an angle going across the SVC. Obviously, you know, with radial velocity, it's relative to the radar, and so if the wind is moving away from you and you have the beam pointed in a weird direction, you're not going to get as much information as maybe you'd want. So if we put the RHI scans as perpendicular to that feature as possible, we're going to get the best information. And it seems like you can approximate the angle of the SVC based on the storm motion, but the storm motion doesn't change too much during the simulation, but the SVC does reorient itself more to the northeast, so we need to look into that a little bit more. But as I mentioned previously, this feature really seems to be important for the parent storm, and especially on tornadogenesis. A few possible techniques for observing this have been presented so far, but it's useful to also have at least some quantitative understanding of what this feature is actually doing to the storm. The SVC, as we've defined it here, begins interacting with the updraft shortly before 3,600 seconds. And from that point, we see a nonlinear feedback process that starts to really enhance the low-level features of the storm. So what this is this box is the area that we averaged 3 different variables: vertical velocity, vertical acceleration, and streamwise vorticity. So basically, it's the average vertical velocity in this entire area for each second between 3,000 and 4,600. And we did the same for all the rest of the variables as well. So this is for vertical velocity, and this line denotes the 3,600 meter isosurface or isoline, whatever you want to call it. And notice that there's a pretty significant lowering of this area of 36 meters per second. The dotted line, it denotes the time of tornadogenesis, and it pretty much, as soon as this thing lowers and starts to level out, the tornado gets going.
What's the black dot for?
That's the time of tornadogenesis. Oh, the black dot? That was something PowerPoint did. I couldn't get it to go away.
There you go. Push it away.
Yeah. So this is vertical acceleration. Again, the black dotted line is tornadogenesis. And notice in the time leading up to tornadogenesis, you see this big increase in vertical acceleration way down at the ground level. And I believe that's got to be related to the lowering of the updraft itself, but you kind of start getting into a chicken egg problem here. Did the acceleration happen first, or did the lowering happen first? Or, you know, there's all kinds of philosophical discussions you can get in about what happens first here. And this is streamwise vorticity. Again, we see a pretty significant increase leading up to the time of tornadogenesis, and you also see an increase in height of streamwise vorticity leading up to this time. This only goes up to 1.5 kilometers here, so it's still a significant increase, but it's not, you know, way up into the storm. But we don't care about way up into the storm. We're all the way at the ground level with tornadoes. This is about 0.4, so almost half a kilometer difference in the height of streamwise vorticity over that period of time, and that's 600 seconds. So it's a really rapid process that happens here. You get the SVC, and then you get lowering and strengthening of updraft, increase of vorticity and magnitude and height, and boom, tornado. It's a really rapid process.
Isn't the streamlined vorticity, when you're in a region of really strong updraft, going to suddenly increase coincident with the updraft? Because the vorticity is vertical, and so is your predominant velocity vector, right?
Yeah, well, so the SVC, it starts horizontal along the forward flank downdraft boundary, and then it gets tilted into the vertical.
Okay.
And yes, you get stretching of vorticity from the increase in magnitude of the updraft, which increases the magnitude of vorticity. So again, it's a feedback process. And you get in, it's very nonlinear. You start getting into which one happens first. It's a mess. But
Yeah, so I'm trying to understand, it's really interesting geometry going on here. That can you track the direction of the vector along which you're measuring the vorticity, and when does that transition?
Yeah, so we can run trajectories through the simulation to basically follow the air as it goes through there.
Mm-hmm.
And it, what was the last part of your question?
Well, it must be, at some point, that direction must point straight into vertical,
Yep.
or nearly so.
Yep.
And it starts out at something nearly horizontal, because there's vertical shear in the environment. So when does that transition take place, and what's it coincident with?
It's like basically right at the tornado.
Okay, so it all happens at once.
Yeah, I mean, the strongest vertical velocity is a very concise region.
Mhm.
And it's like, you see this, in the animations, you can see this horizontal vorticity come out of the forward flank, and then it hits the updraft, and it's just like, boom.
Straight up.
up.
Okay.
Yeah. It's
That's
really
interesting.
quick, most of the time, especially once the storm really gets strong. In its weaker stages, you can kind of see some, weaker vorticity that takes a little bit longer to go vertical, but it's not by much. It's
Yeah.
still really fast. We haven't quite proven that all these quantities are the causal factor of tornadogenesis. We still need to do more quantitative analysis, but it does suggest a feedback process, and that feedback process eventually culminates in a tornado. The MVT that we were talking about earlier is present during all this time. And the NVT conglomerating with the main updraft center, and all these enhancements are taking place simultaneously. And so if you view the supplemental animations that were provided with Lee's paper in 2017, it's very obvious that these minds of vortices eventually become the tornado. I know it's harder to see when I'm giving you stills, but in the animations it's very clear. But the NVT doesn't conglomerate randomly. It works in concert with these other processes. The strength of the updraft, it really seems to reach a critical point that drives vertical vorticity to coalesce. And there really appears to be no identifiable trigger. Like I had mentioned before, it's just everything reaches a critical point, everything starts to coalesce, and then it happens.
Austin, can you imagine it would be fruitful to look at a case where, though you have a meso-vortex train that's identifiable with your analysis, it does not result in a tornado?
Oh, absolutely.
And you haven't been able to do that yet, right?
No,
But-
I mean, that's just more worms in the can.
Yeah.
But
Something doesn't happen to those worms
yeah,
in that case compared to the strong
yeah.
cases.
I'm sure there's cases of that.
Yeah.
But yeah, that would really be interesting.
Have there
You know-
been simulations of non-tornadic storms like this at this resolution?
Yeah, Lee has run some that have, we're calling them failure cases. Either they don't produce a tornado or they produce a very short, weak tornado. And like I said, we're probably going to analyze at least one of those to compare it, make some similar images. But yeah,
I'm
it
going to
remains
suggest
be
that's
seen.
something that goes in the thesis, that we have a null case to at least side by side with one of these cases. I think that would be strengthen the work a lot, because it would be nice to not just see what one case looks like, but what one case doesn't. When you don't have that.
And I wonder if you do those side by side, I'm guessing you don't still see the trigger, right? You may not see the trigger in the case, but when you look at it in the case where it doesn't form, will a trigger be apparent in the comparison?
Well, yeah,
Maybe.
because the trigger may not be a feature, it may be a collection of circumstances
Yeah.
that you don't identify except by comparison,
Yeah.
because that's
Yep.
perfectly consistent with the philosophical view of a cause and effect.
Yeah, no, and I really like the way you worded that. It's a collection of circumstances. It's basically what leads to the tornado, in this case at least. And I should point out that in this simulation, we're specifically talking about violent, long-lived tornadoes, which are a very different breed. from short-lived weak tornadoes. There could be entirely different modes of genesis for the weaker, shorter-lived tornadoes. So this is just one very specific facet of tornado science.
Yes.
Violent tornadoes make up over 70% of all fatalities related to tornadoes, so it's important that we're studying a specific problem, even if it is a very small facet of the science. So I think further investigation of the SVC is undoubtedly warranted if they continue to show up in these future simulations. And we do have some other simulations of different storms in different environments that produce a similar looking feature. They don't quite do the exact same things, but it is very similar. I think there's years of work to come out of this. Everyone in the lab does too. I think we could sit on this 30-meter simulation for 20 years and still figure stuff out. But of course, Lee is a supercomputer genius and wants to push it to the limit. So now he's running 10-meter simulations. I also think the MVT, which was not an original focal point of this study, and it later became one as it became more and more apparent that it was important. I think the MVT is something that should also be a very big focal point for tornado research moving forward. I think it would be incredibly beneficial to improving the forecast process if we could discern what environments produce SVCs that also produce a subsequent MVT. I think if you could figure those two things out, we're really going to make a great step in the right direction as far as forecasting these types of storms. So we determined that the SVC's interaction with the storm appears to have a significant impact on its evolution, especially through enhancement of the low-level updraft. These enhancements, when they work together with the MVT, they seem to reach a critical point or a collection of circumstances where the strength of the low-level updraft results in a conglomeration of these mesovortices and eventually becomes a tornado. Evidence of the SVC, including these mesovortices and the MVT, are visible on these radar scans that I've emulated, especially at the higher resolution. And the RHI cross-section shows a signature that closely resembles the rotors that are found on thunderstorm gust fronts. And I believe the optimal RHI scanning strategies to find this feature would be perpendicular orientation. There's been evidence in nature discovered now of a kinematic boundary that resembles an SVC in Paducah, Kentucky. It looks very similar to the images that we made with our radar emulator. And this is encouraging for operational detection, but it'll likely, again, be a very rare and conditional instance. I think until operational radar technology improves, we're still a ways off from seeing this thing at the forecast desk. I'm really hoping that this research, if we can get it published, inspires some more field projects that are based on finding this feature. There's one that actually just finished that looks like it's going to be really awesome. But if they don't completely solve the problem with that field project, I hope that this will help aid in future efforts. And with that, I want to say some thank yous first to my wife. I would not have made it this far without her, that is a fact. She has been basically my encouragement and support over the last several years, and I really hope I've been as good of a teammate to her as she's been to me. I wish she was here today, but her mom is here in her place. So. I also want to thank my family and my friends for the encouragement. A huge thank you to Lee, who really took a chance on me, knowing that I wasn't a super computer nerd like Kelton is. But he's really given me the ticket to live my dream and study tornadoes. I've wanted to do this since I was a little bitty kid. So can't thank Lee enough for that. Couldn't have asked for a better advisor. Thank you to Steve and Grant for being a part of my reading committee. And lastly, I want to thank all of AOS for my experience here from a master's degree. It's really been wonderful. So with that, I will take any questions. Grant, go ahead.
Yeah, you talked about the benefits and limitations of PVI versus RHI scans and these features. What about dual Doppler? What if you had two Doppler radars operating for a particular feature? Would the three-dimensional information you got out of that be helpful in discerning things?
Absolutely. Yeah, the SVC is a very three-dimensional feature. The closer you can get to seeing it in 3D, the better. Absolutely, and we've talked about that. It's just, since it's an emulator and not a simulator, putting two cones of silence in there isn't going to change anything. You know? But yeah, I think that would absolutely be useful.
So why upgrade the operational radars, given what you were just saying, as opposed to then National Weather Service investing in a couple of high-resolution research radars that they then just send out when there's a storm?
I think the resources it would take to build that many mobile radars and the organization and planning it would require from each weather service office would be more of a hassle than upgrading the radar network that we currently have. But that's just a speculation.
I have an alternative to that where you just take the simplest map of like Tornado Alley and you decide that in certain locations in the United States, the upgrade is going to involve pairing Doppler radars, like at Oklahoma City, like in Goodland, Kansas, some other places, so that you have built into your observational network dual Doppler capability for the places where it's most likely to matter.
Yeah.
And so that'd be one thing. But the other thing I wanted to ask you, Austin, for your opinion of, you're right. I think that you could spend forever on your 30-meter data set. Because I think what you're doing so far is you're able to say, the analogy I have in my mind is, you can say something about the offensive potency of a baseball team by knowing everybody's batting average. But you can really dig in if you can find out, why is this team with batting averages that look like everyone else, why are they so good at winning games in the last 3 innings? You find out that certain people hit really well when the count's 1 and 2. Certain people hit well on 3 and 0, all sorts of things. Those are details underneath the hood that you could keep on mining out of what you have. It'd be, going back to tornadoes it was, and thinking about what is it that allows, the collection of environmental circumstances to drive these things into this extreme tornado category versus, you'd have to do other simulations, but of the weaker ones that don't fire off. You could spend your whole career doing that, and it would be a worthwhile career, it seems to me.
Yeah, that's the question. Why do some storms produce long-track violent tornadoes, and why does the supercell that looks just as gnarly just to the south of it not do anything?
Yeah.
It's very interesting small-scale details that make the difference, I think.
One of the challenges, I think, as Austin's advisor, is to only give him a master-sized piece of this to chew on, because we could go crazy, and it's like we have all these ideas, but we gotta keep it small.
No, that's right.
I think one of the hardest parts of
service.
One of the hardest parts of writing this paper was finally deciding on what I wanted to focus on, because there was 100 different things I could have said.
Yeah, I can see that. That's a definite problem.
Yep.
On the topic of the tornadic versus, or the violently tornadic versus not, but still looking like a strong supercell, what's your intuition on the presence of an SVC in either of those cases? Like, do you think that it's something that's present in all supercells or a subset, or?
I think it's present in most strong supercells. And all supercells are strong storms, but there are definitely ones that are stronger than others. I think once you get one, you're going to get a really stout updraft. So in cases where you have large hail, even if you don't get a tornado, if you have, you can still have a really strong updraft. I think those cases where you have the really bad, severe supercells, they probably have SVCs. But I also think there's probably a small subset of them that maybe don't have one, or maybe don't have one like we see here, maybe a smaller, weaker one. Yeah.
Follow up on that, what would be a threshold for calling something an SVC? Because obviously most supercells have extreme-wise vorticity and forward flag. Most of them have some type of rotation, but at some point it becomes like it has a feedback on the storm at some point. It's on critical threshold of strength or magnitude or whatever. Is there a threshold that you would?
So I did choose a threshold in the paper. The problem is I chose it with temporally average data, and so it's a little bit skewed, I think, the numbers, but using the temporally averaged data, if you looked at the time the SVC really starts influencing the storm in this simulation, which is 3,600 seconds. Yeah. The SVC, when it's temporally averaged at that point, the streamline vorticity magnitude is around 0.1 per second. And that was the magnitude I chose, and basically said, all right, once we reach 0.1 per second, on average, we have an SVC. And from that point forward, analyze it from there. Grant?
Yeah, this may be as much a question for Lee as it is for you, but you talked about going from 30 to 10 meter resolution. The 30 meter already seems incredibly detailed to me. What do you expect to see at 10 meters that you can't see at 30?
Yeah, so this is part of, the only way I can get more supercomputing time is to say I'll do more great, awesome things. Oh, seriously. So what I'm seeing in 10 meters is, A, we're getting more convergence of solution. Everything from, I've done 30, 20, 15, and 10. They all have SVCs, they all have multiple vortex, long track EF5 cyclonic tornadoes. At 10 meters, you are resolving the subvortices, the suction vortices, and you get the beautiful scallop cycloidal patterns underground and everything like that. So if anything, the 10-meter simulation is telling us more about the tornado, whereas the 30-meter simulation is perfectly valid at just studying the supercell, I would call them microdynamics, whatever you want to call it. And the nice thing about the fact that we're getting somewhat of convergence is we don't have to look at 10-meter data for everything, because it is a lot of data, it is a lot of noise, and I'm going to have to average things anyway just to get an idea what's going on. So the benefit is, and here's another thing that is interesting, but the SVC per se becomes much more turbulent, as you might expect, as you get to higher resolution. So it's not necessarily this nice smooth, it's not as smooth as the 30-meter simulation. It's funny because I always used to think of those old, 2-kilometer supercell simulations looking with lava lamps. Now I look at the 30-meter simulation, and it looks kind of lava lampy to me, but that's crazy because no one else is doing any kind of high resolution work at this scale. So the answer is, I think, like, we can get a lot out of the 30-meter simulation. The higher resolution stuff is going to be analyzed as well. It's just, right now I'm collecting data, and what we do with that data, we'll have fun with it, but it remains to be seen what benefit we really get from these super high resolution simulations. Mostly what I see is getting the tornado dynamics better, which I think is of value.
We're back.
So I'm just curious, what's like the context in terms of the broad literature on tornado genesis and like the role of SVC specifically? My knowledge comes from essentially people in this room.
Mm-hmm.
And there's kind of a chicken and egg problem that you alluded to, where you're seeing a co-location of all these things that produce a tornado. Is there any way to do like some sort of, I think of it as like potential vorticity surgery or something, where you removed just the SVC and then redid the simulations, or would that just be impossible?
So the problem is with that is that we don't touch the simulation after we perturb the environment. So basically, and Lee could correct me if I'm wrong, but we basically put in the model sounding, perturb the environment, and we don't touch it. It does its own thing. And so, I don't know, maybe if you took a restart file and just clipped it out or something.
Yeah, that's kind of what she's saying.
Yeah.
That
Approach makes sense though, because it's basically like removing the heart, liver, lungs of your supercell, and then saying,
oh, gee, the tornado didn't.
The storm itself is just going to collapse, and you wouldn't have anything to maintain the updraft.
But you can learn from restart files and perturb the environment to see how it affects things. So we have the ability to do that, but I would never probably do it in a PV inversion framework. I don't think it would really. I don't know. I can't wrap my brain around how that would apply to this kind of simulation.
Yeah.
But definitely, sensitivity study of different things is possible if we're clever about it.
Yeah.
And I haven't really considered all this. And can you kill the SVC? Can you kill the tornado? Can you do something that causes that accumulation of things to not quite make it? Because those are the fascinating cases, or when you don't get the tornado in a very similar environment as when you do. So the answer is, yeah, it's on my list, something like that, personally, but I don't know if it's going to be that particular approach we take, but something perhaps similar in perturbing the environment from the restart file.
And as far as the literature goes on SVCs, it exists in this room, pretty much. So there's not much. Yes, Pete?
Real quick, looking for these features in radar, the SVC and the mesovortex train, is all basically done visually by you looking at imagery. Is there any hope of using like machine learning or multi-dimensional, looking at the evolution in time or the evolution, vertically or whatever in terms of identifying these features in either research or radar data through like machine learning or an algorithmic
Well,
way?
that takes the fun out of it, but yeah.
Well, but I mean, it might give you an idea, it might give the person sitting at the forecast desk something to look at rather than just,
Yeah, they're already doing that in
Yeah.
the operational forecast sector. They have a program right now called multi-radar, multi-sensor, where basically they're making machine learning algorithms for detecting important features on radar, and that's absolutely something that could be done in this.
Part of the problem is you need to have a set of data where you have it already defined it, you've tagged it, you've had
Right.
several, hundreds of examples of SVCs
You
or
have to tell
whatever.
it what to look for.
Tell it what to look
Yeah.
for. And there's different ways to do AI, and we're just as a community starting to really wrap our brains around AI. There was a recent conference, first conference that, where they had this, Noah hosted it, I watched it virtually. It's fascinating, there's all these different ideas. But one of the things that I came back from that is that you need to tag data. You need to tag simulations. This isn't, a supercell. It does not produce a tornado. Here's the weak echo region in a tornadic supercell, non-tornadic, strongly. And until you can do that, AI doesn't just make things out of nothing. It has to sort of use mine data that's already been given some guidance that I
right,
should
but,
know.
but given the fact that you're able to move the radar location and see it better, the information might be there if you look for it in the right way.
Yes.
Mhm.
I guess that's what I'm getting at.
Yeah, absolutely.
We only have one storm and one storm, one environment. That's what concerns me. We need to look at a whole bunch of different storms because it's tempting to draw great grand conclusions from a single wonderful simulation, or maybe even two. But until we can apply this to more storms, that's what I think.
But you do have the encouraging observation
Yes.
that Paducah storm
Yeah,
did show
right.
it.
But the Paducah storm produced a tornado. It was EF3, I think. Was there an SVC? Well, what we saw was a nice radial velocity signature that matches what we see. But is that an SVC or is it just some jet? You know what I mean? We don't know for sure.
Yep.
So
It had a very similar curve in it.
yeah, I
What
saw
was
that.
really
I was
encouraging
really-
to me because
I know.
the SVC does that
It
wrap
does the
around.
curve because it goes,
Right.
lifts up and goes up. That's right.
Did I see some other questions? Yeah.
You talked about identifying critical points, and you also talked about how prior to the actual tornado, it was fairly turbulent and then it relaxed itself. You kind of looked at aerial average statistics, that it was in a big box?
Yep.
Poorly average.
Well, the
He's
box,
talking about
Oh, I'm
the
sorry.
aerial
Yeah,
average one?
time
yeah.
height
Yeah.
stuff.
To me, it seems like you're kind of, it's these meso vortex chain is sort of like a chaotic system,
Mm-hmm.
and somehow you're reaching a point where you're going into a potential block.
Yeah.
Hmm.
Kind of an
Thought about a
equilibrium.
way to pull out, and it's clearly that system is confined to this flank of the SVC.
Mm-hmm.
Have you thought about looking at the statistics of the simulation just along that kinematic barrier? And maybe look at, variance and mean, thinking about something that's moving around in orbit and eventually collapsing into a potential well, but that potential well might be defined out.
Yeah, so what kind of statistics were you thinking?
I don't know, I'm just saying, maybe, it seems like you're going the right direction looking at a box,
Mm-hmm.
but I would define it on more of a,
More of a band?
on some kind of, you identify this kinematic surface.
Right.
Do the statistics on that.
Yeah.
Look
Yeah.
look at variance,
Mm-hmm.
because I bet your variance is gonna collapse.
Right.
One thing that I would mention is that you said the FFDB. There's actually several boundaries along the forward flank.
Right.
Neither one of which is the FFDB in my opinion. You have a diffuse sort of region that's out in the forward, is the easternmost part of the forward flank that I think is primarily from melting hail. I'm not exactly sure microphysically what's going on. Then you have these internal boundaries where you see like a 2 or 3 Kelvin theta rho prime or theta prime boundary right there, and that's where the SVC seems to line up.
Yeah, it lives right along that strongest boundary.
Typically, the FFDB isn't a north-south boundary, but an east-west boundary. So, but I would say when you refer to that boundary, maybe not call it the FFDB, but call it, it is a some. Yeah, I don't know exactly what, but other people might look at you a little funny. But there's definitely these baroclinic zones in the cold pool. The cold pool is extremely complex and turbulent.
and eventually becomes less so, as Brad was saying. My perspective is it's when the updraft goes crazy, everything just kind of lines up. But it's really what's causing the updraft to go crazy that's really, I think, where the best science can be done. What is leading to the updraft going crazy? Because once you have that updraft going crazy, it just slurps everything up. The MVT that you see, those vortices essentially are growing out of the ground. They're getting stretched. They're moving into a region of DWDZ going crazy. So of course, they're stretching, you have vertical advection, and they just kind of do that, and then they fold in. So it's the updraft. It's just, but yeah, so that's, yeah.
No, that's a good point. I mean, I kind of got confused with the forward flank downdraft boundary thing myself, because it's like, you have all this other rain out here, but then why do we have this like really strong gradient that just shoots up into the forward flank?
Exactly.
It's like,
it's all in the microphysics, and
Yeah.
God, I don't want to go in there, but we're gonna have to at some point.
My job.
any other
All right,
questions?
so we say thanks, and then the committee can stay around?
Yeah, sounds good. Thank you.